So let's see, this example here we'll probably spend the rest of the time talking about it today. So this example is something called a current lead. So let's say you have some experiment, some of you guys in here might do this type of thing, where you have a cryogenic application. And you have the need to get electricity or some current from room temperature through a wire down to your cryogenic device. And that cryogenic device is at 40 Kelvin, which in terms of cryogenics is actually not that cold. But when you're looking at the conduction across this wire, it can be significant because you have such a big temperature difference, right? 300 down to 40. So there's some properties here. You're flowing electricity through this. There's electrical resistivity associated with the wire, meaning you push current through it, it's going to generate heat. So this problem actually has thermal generation along with it. This application is high current, so you have 1,000 amps you're trying to put through this thing. So the heat that you're generating is really important, and you have to figure out how much of that heat ultimately is getting into my cryogenic device, which is something I have to pay money to cool down, right? So I'm trying to minimize at this interface down here how much heat is going from just on this side into the device, right? Let's see, some loose ends. We've got contact resistances on the top and bottom, and we're given some geometry. So let's go through how to do this. Again, now we have a cylindrical geometry. Right? This isn't shown, but it's a cylindrical geometry. You have the length is much longer than the diameter, right? It's not drawn to scale. And we're going to do this with a numerical solution, including generation. Okay? All right, so the first thing we're going to do is, what was step one? So one was define n nodes. All right, so we're taking our domain, which is in this x direction, and we're going to break it up into an equal number of segments. All right, I've got n here. N could be any number we want. But what you'd want to do is you sketch out your domain and then sketch where each node is positioned. Right, the first thing to note is that the n nodes coincide with the domain boundaries. Right, that means I've got the node actually positioned on the edge of the domain. Some meshes that you would do, the node would maybe be offset, so the control volume around the node is coinciding. For this type of a finite difference problem, you're always going to want to have, or usually going to want to have the node on the interface. And why is that? Well, because I have to enforce boundary conditions eventually. It's much easier to enforce a boundary condition on a node than on some distance from a node, right? So we'll put the nodes on the boundaries. Okay. Part of this is also figuring out the position of each node. So we're going to define this position called x sub I. And x sub I is going to be the location of each node in the domain. And we would say, let's see, so this is going to be, first of all, let me come over here. So what is delta x? What is the distance between each node? Remembering that the nodes are on the boundaries. That's going to be the total length, L, divided by how many segments are present. That's n minus 1. All right, I've got n minus 1 gaps that I have to account for. So that's my delta x. All right. So then the position of each node is going to be xi is, let's see, I minus 1 over n minus 1 times L, right? Or it's I minus 1 times delta x equivalently. So why I minus 1? Again, look at what this is saying. If my first I index is 1, then my first x position needs to be 0, so it would just be 1 minus 1 is 0. Okay? So this should account for all the positions in the domain. That leads us to step 2, which is doing for the first law on each control volume. All right. So here on the bottom, I have drawn some node I. And in some node I, you draw a control volume around that node. And the way to draw it is you're going to have the boundaries of that control volume be halfway between the node that you're trying to model and the adjacent one, right? So you have this width delta or length delta x control volume, but it's centered around the node. So we've drawn that. We need to take inventory of all the stuff that's first law related. So again, this is a little hard to see, but always, let me just make this note. So we're going to always draw heat flowing in, right? So what I'm saying is you have heat flowing from the top into this node. You potentially have heat flowing from the bottom into this node. You have thermal generation. And let's say we had something with the surroundings, which we're not modeling here, but we draw it flowing into that node. And the reason we're going to do that is it really helps us with bookkeeping. Right? We have to repeat this process for every single node. So ultimately, we just have to make sure that the sign that we write in our equations matches the direction of the arrow, and everything will work out. But it helps with writing the equations, with bookkeeping, to have everything drawn in. Okay, so just remember that, flowing in. All right, so we've got our control volume. So let's write out the energy balance. It's going to be Q dot top plus Q dot bottom plus G dot is equal to 0, right? Incidentally, this is for node I, right? You have to repeat this for every single node. So we could add subscripts on that to say I. We'll do that later. Step 3 is use rate equations to approximate each term. So let's start with Q dot top. All right, so Q dot top, comma I, is going to be, let's use a resistance approximation to calculate this. So we have the driving temperature difference is going to be T at I minus 1. Right, we're starting at this node, and we're going to this node, so then it's minus Ti divided by the resistance between those two nodes, right? And the resistance between the two nodes is going to be the conduction. It's basically a plane wall conduction, right? Because we're going in the direction axially. So that becomes, Ti minus 1 minus Ti times K times AC over delta X. Right, does everybody see where that came from? Right, this here is 1 over resistance. Thickness or length over KAC is the resistance. So we're, 1 over that is our resistance here. And it's between the two nodes. So it's the delta X is the distance that we're conducting. Right? And AC, I know people are going to mess this up, right? But AC is this area that's normal to the direction of flow. Okay. So that's Q dot top. Let's see, Q dot bottom. I is very similar. The only difference is we have Ti plus 1 minus Ti times KAC over delta X. This is basically the same thing. It's just that we're starting at Ti plus 1 and then going to Ti. All right, and then let's see, we still need generation. So we have thermal generation occurring. So G dot I is equal to the resistivity, rho E, times the volume of, oops, what's going on here? Times the formula is this. So it's resistivity times delta X over AC times the current squared. That's the generation. So you could go look that up somewhere. But again, the volume that it's corresponding to is delta X here. Okay. Questions on this part so far? Okay. This equation that I've written, what are these equations valid for? Which nodes are these equations valid for? Right. So that's going to be valid for I equals 2 up to n minus 1, right? So I now have n minus 2 equations. I just duplicate this set of equations with this energy balance n minus 2 times, and I've accounted for almost all of the relationships between nodes in this body. What I'm left with is needing to do the same thing on the n nodes, right? You need to also come up with energy balance and repeat this process for the n nodes so that you can come up with your 2 additional equations that you need.